Hi everyone. What I wanted to do in this video is give a brief review of our Test 3 material, which covers everything from Test 2 up to and including the end of randomized complete block designs. So where we left off at the end of Test 2 was looking at simple linear regression, which progressed into multiple regression. Then a linear regression in general is considered a mathematical model in which we assume a straight line relationship between a continuous response as well as one or more explanatory variables, sometimes called predictors. So in simple linear regression, or SLR, we assume that there's only one predictor and that the mean response, mu sub y, is equal to beta naught plus beta 1 x. X may be continuous or it may be a categorical variable. Sometimes it might be an indicator variable. If there are several predictors, so say p predictors, then we're in the realm of doing multiple linear regression, where again, we assume a linear relationship between the mean response mu y and multiple x's or predictors. So that's equal to beta naught plus beta 1 x1 plus beta 2 x2 all the way up to beta p xp. In the regression model, the intercept, beta naught, is or can be interpreted as the mean response when all x's are equal to 0. So if we're in the case of simple linear regression, that's like saying if x is equal to 0, then the second term drops and we're left with b naught. In multiple regression, all x's are equal to 0, so all of these terms drop and we're left with beta naught. Beta j, on the other hand, is the change in the mean response that's associated with a unit increase in xj, but all other x's remain constant. Okay, so what can we do with a regression model? Well, let's first focus on the special case where p equals 1. So that's that simple linear regression setting. And there we can calculate explicitly estimates for beta naught and for beta 1. So we start off by B1, which is the sample estimate of the slope parameter, is equal to Rxy over Sx, where R is our sample correlation, and B naught is equal to Y bar minus B1 X bar. So these are things we can calculate from our data. Associated with these models are also the residuals, which is basically our estimate of the errors. So we, instead of using errors, we use epsilon, our residuals, we have EI is equal to YI minus YI hat. So that's observed minus predicted. And here's a little plot of some sample data, maybe what the regression line might be. So this one is the line y equals b naught plus b1 x. And this dot right here, or I should say this point on the line, might correspond to a fitted line. So if x were equal to this value, then this would be yi hat. The point on the line would be our best guess of the response, but it might have actually been the x that's up here. So that's the yi, and this gap is the residual. So that's the error in our prediction. This regression line is found by least squares. We don't go through the theory, but it's through this method we end up getting the estimates for or the formulas for B0 and for B1. But by virtue of being a least squares regression line, we're minimizing these squared deviations from the line. And then that also gives us a way to think about how to estimate the standard deviation that's associated with the errors. So we use S in the sample to represent that, and it's just the square root of the sum of the squared residuals divided by n minus p minus 1, which is the sum of squares error over n minus p minus 1, where p equals 1 for simple linear regression. And we can also proceed to look at the sum of squares total and then decompose that into, or partition it into, a sum of squares due to our regression model and sum of squares error. So depending on software that you use, sometimes it will say model and error, sometimes it'll say regression and residual, or regression and error, and so forth. But the point is that due to our regression model, we have associated with that p degrees of freedom. P is the number of predictor variables. The error has n minus p minus 1, which can be found by subtraction because the total sum of squares is n minus 1. So the degrees of freedom partition and the sums of squares partition. And then we use sum of squares model, sum of squares error, sum of squares total. If we look at the ratio of the sum of squares model over its degrees of freedom, we get the mean square model. And similarly so for the mean square error. Turns out that this mean square error gives us an estimate of that error variance. So the sigma hat square. And then if we look at the ratio of these mean squares, so mean square model over mean square error, we get an F statistic. And now we're in business to do some type of inference for our model. So the first type of test we might be interested in doing is an overall, or the ANOVA F test. Which tests that each of the betas are not only equal to each other, but that are equal to 0. So the null hypothesis is that there are no slope parameters. And the alternative is that at least one of those slope parameters is non-zero. The F statistic can be read off of our ANOVA table, and it has been shown that under the null hypothesis, so this is under H0, it follows an F distribution with P numerator degrees of freedom and N minus P minus 1 denominator degrees of freedom. And then the p-value for these F tests is always a one-sided p-value. So it's the probability that F, which has these degrees of freedom, is greater than or equal to our observed test statistic. For simple linear regression, this test is equivalent to doing a t-test on beta 1. In particular, if we looked at the two-sided test with a null hypothesis that beta 1 is equal to 0 versus the alternative that beta 1 is unequal to 0, then our test statistic is just the ratio of B1 over its standard error with the degrees of freedom equal to n minus p minus 1. And since it's a simple linear regression, p is equal to 1. So degrees of freedom is just n minus 2. So here's the relationship between this test statistic and the F observed. It's that the F observed is equal to the square of this test statistic. So if you numerically calculated this t from your data and you calculated the F observed from your ANOVA table, you should find that this relationship holds. And now our p-value is 2 times the probability that t is greater than or equal to our test statistic, the absolute value of our test statistic. So those are equivalent, but if you were performing a test on your slope parameter, you could also do a one-sided test. We just have to remember that the p-value changes accordingly. So it depends on what the alternative hypothesis is. If you look at your ANOVA table, you could also take the ratio of the sum of squares model over the sum of squares treatment. And this ratio, it gives us what's known as the R-squared value. The R-squared value tells us what proportion of the variation in our response y can be explained or attributed to our regression model. And what's nice about that is that in simple linear regression, that capital R squared is in fact numerically equal to the squared correlation as well. So that correlation between our explanatory variable and our response variable. And remember, the correlation is basically a measure to the extent that there is a straight line relationship between the two variables. So in the general setting, although this works, and what I'm about to say, it works if you just set p equal to 1, so you're in simple linear regression, or p is greater than 1, in which case it's multiple regression. So we have our test statistic beta j equal to 0, or sorry, a null hypothesis that beta j is equal to 0, has the test statistic bj over standard error of bj. So this is exactly the same as what we did on the previous page where we were specifically talking about simple linear regression. And the degrees of freedom is inherited from the mean square error. So it has n minus p minus 1 degrees of freedom. The p-value depends on the alternative. But once we've done these, we have all the bits almost all the bits we need to build a 95% confidence interval for the slope parameter. And that would just be our estimate of the slope parameter, bj, plus or minus t star times the standard error of bj, where t star is based on our n minus 1 minus p degrees of freedom. In the case of simple linear regression, we also talked about a few other types of intervals. So we could also think about building a 95% confidence interval for the mean response. So if we were to randomly select a unit from our sample, our best guess at the response for that individual, for the mean response, would be y hat plus or minus t star standard error of mu hat. And in here, what we note is that the best guess given our model, so the best guess of the mean response is the predicted value. These two things are equal. So this should be, you could think of it as mu star plus or minus t star standard error, but mu hat is equal to y hat. On the other hand, we might be interested in building what's known as a 95% prediction interval. So that's like a confidence interval, but it's for a future observation that is not in our sample. Again, the best guess at the response for that individual would be y hat, which is from our regression model, plus or minus t star times the standard error of y hat. So these two intervals look similar because they're both centered on y hat, and the amount by which they go out depends on t star, but the standard errors are slightly different. The main one is that in here, this is based on your S, and then there's a square root with some other terms in it. The y hat has an extra 1 in it. So that's the main difference between these two. And in the case of simple linear regression, remember that the B1 is written in terms of R. So it turns out that if you wanted to do a test on the population correlation rho, that then that test, the test that rho is equal to 0, is equivalent to the test that beta 1 is equal to 0. So if you only had information on rho, on the sample correlation R, but you wanted to test for a 0 slope, you could do the test on the correlation itself. Or on the other hand, if you only had output then that allow you to do a test on beta 1, you're implicitly doing a test for rho. So if you look at the test statistic that you get from doing the test on rho and the test statistic for doing a test on beta 1 in simple linear regression, when you numerically calculate that from data, you should find that your test statistic is actually equal to each other. Right. One last point that we didn't make with these linear regression are some of the assumptions. So whether it's multiple or simple linear regression, we're assuming that there's a straight line relationship between our response and the x's. We're assuming that our errors come from a simple random sample of a normal 0 sigma square, where sigma square is a constant variance for all observations. And those model parameters were beta naught, beta 1 up to beta p, as well as sigma square. So in the discussion that we just had, we talked about how to estimate all of the betas as well as your S squared. So this is in a simple linear regression setting. But then we moved on and said, well, what if we didn't have a binary or a continuous explanatory variable? What if we wanted to look at the relationship between our response and a categorical treatment variable? In one-way ANOVA, we can model this relationship without making an assumption of linearity. So the analysis of variance is where we get the term ANOVA from, and it decomposes variation in our response into the variation due to the categorical variable, sometimes also known as the between group variation, and the error, which is often known as the within group variation. So our ANOVA model looks at each value xij is equal to mu I, where this is our treatment effect, plus some individual error, epsilon ij, where I is equal to 1 to capital I treatments, and j is equal to 1 up to ni, where there are ni samples or observations for the ith treatment. Just as in the regression setting, we assume that our errors form a simple random sample from a normal 0 sigma square distribution. So sigma is constant variance. And in order to estimate this, what's best to do, even though we assume that the means might be different in each of these populations, we can still pool all our information again for estimating our sigma. So the pooled estimate, we use the small p to denote the pooling, is a square root of the sum of the ni minus 1 si squared, where si is just the standard deviation for the ith treatment group, divided by capital Ni minus I, capital I, where capital N is just the total sample size. So what does our ANOVA table look like? Very similar to what we've looked at before. We have our groups as one of the sources and the errors. So these are the between and within respectively. Our degrees of freedom are I minus 1 when there are capital I groups. There are total N minus 1 degrees of freedom. And so for error, by subtraction, we can find that there's capital N minus capital I degrees of freedom. We can also calculate our sum of squares group, our sum of squares error, and sum of squares. Those should sum up to the sum of squares total, because that's the partitioning that we're doing. And then the ratio of the sum of squares over the degrees of freedom gives us the mean square for the groups and for the error. And the mean square error is, in fact, the pooled estimate of variance. And then when we take the ratio of the mean square group over mean square error, we get our observed test statistic, F. So now we're in business to do an overall F-test, where the null hypothesis is that all of the group means are equal versus the alternative that they are not all equal. The observed test statistic can be read from our ANOVA table, and it follows an F distribution with I minus 1 and N minus, this should be capital I, degrees of freedom under the null hypothesis. And then the p-value is equal to the probability that F is greater than or equal to our observed test statistic. So these degrees of freedom, again, can be read off of our ANOVA table directly, because they're the ones that our mean squared terms are also based on. In one-way ANOVA, we can also calculate R squared, which has the same interpretation as in regression. And remember, R squared is equal to sum of squares model over sum of squares total. So we can interpret it as the proportion explained by our model. But now we call it a coefficient of determination in the one-way ANOVA setting. We can also calculate contrast, because remember, when we do this overall F-test, we can determine whether the means are equal or not, but then we don't have any information about which ones differ or how they differ. So this, if we have specific treatment group combinations we're interested in, we can use contrast to do that. And at the population level, we use the letter psi to represent a contrast. If, for example, we wanted to compare group 1, so the first one of the groups, to the rest of the groups, then we usually take that particular group minus the average of the other means. So if I equal to 4, we might be interested in the contrast mu1 minus, there are 3 other means left, so 1/3 mu2 minus 1/3 mu3 minus 1/3 mu4. So this is basically giving the average of mu2, mu3, mu4. But once it's written in this form, we can see the coefficients of our contrast is given by A1 equals 1, and then A2 equals A3 equals A4 equals minus 1/3. And we can also check that it is a proper contrast because the sum of these AIs are equal to 0, or is equal to 0. We can perform hypothesis tests on the contrast. So the null hypothesis being that the contrast is equal to 0. That would be using a test statistic T, which equals C over the standard error of C, and our degrees of freedom would be capital N minus I, because the degrees of freedom is inherited from the mean square error, which is based on N minus I degrees of freedom. We could also, and then the p-value depends on what the alternative is for your hypothesis test. Or we could also build a 95% confidence interval for psi, which is given by C, so that's the sample estimate of the contrast, plus or minus T star times standard error of our contrast. Again, T star is based on that N minus I degrees of freedom. But sometimes we're in a situation where we don't necessarily have a specific contrast that we're interested in. We actually just want to do all pairwise comparisons. In that case, we may have to start considering, particularly when there are many groups, we're probably interested in looking at these multiple comparison, or making multiple comparisons with a family-wise type 1 error rate of alpha. So that at this alpha level at the family level. And the way that those tests would work is that the null hypothesis is that mu I is equal to some mu j, where I and j are not equal, versus the alternative that mu I and mu j are not equal. The test statistic, we use Tij just so we know that it's I minus j. is equal to x bar I minus x bar j divided by, and then the standard error for that difference is SP times the square root of 1 over the sample size for the ith group plus 1 over the sample size for the jth group. And again, it's based on n minus I degrees of freedom because it's inherited from this SP. So we haven't done anything to do, commented on the multiple comparisons up to this point, but to do the multiple comparisons, we have to decide whether we're interested in doing the least square difference, which effectively ignores the multiple comparison, or the Bonferroni method. So the least squares difference says reject H naught if the absolute value of our Tij is greater than or equal to T star, which is the usual T star we use based on our n minus I degrees of freedom. The Bonferroni method adjusts for the multiple comparisons by saying if we want an overall type 1 error rate of alpha, then for each individual test, we need a smaller alpha level. So there, we reject H naught if Tij, the absolute value of it, is greater than or equal to T star star, where T star star is a critical value based on n minus I degrees of freedom, and alpha star star, which is alpha divided by the number of tests. There are actually many different multiple comparison approaches, but the Bonferroni one is an easy one and easy to understand as well, and easy to calculate. If we're worried about these multiple comparisons, we can also build 95% simultaneous confidence intervals for those differences. And the confidence intervals, or simultaneous ones, look at the difference between our sample means plus or minus T star star, which is what we get from the Bonferroni method, times the standard error for the difference. And of course, can't forget that a T star star value comes from our software. Okay, so we don't, in general, it's hard to calculate the T star star from our table D. Okay, so we've looked at this one-way analysis of variance, but what if we were interested in looking at the relationship between our response and this categorical variable, but there's another variable that is known to be related to the response. And so we know, okay, we should account for it in our model. Otherwise, if we see differences, we don't know whether it's because of our variable or because of this other variable. So what we can do is block on it. In other words, we group our units into capital B blocks, where each block has I units, and then randomize units within the block to one of the treatments. So each observation in a block has one observation in each block is assigned to each treatment. So then our ANOVA table is a little bit more expanded, because now in the source we have our blocks, our treatment, and our error, with B minus 1 degrees of freedom for blocks when there are capital B blocks, capital I minus 1 degrees of freedom for treatment when there are I treatments, and capital N minus 1 degrees of freedoms in total. If we look at the difference, it turns out that it's also equal to I minus 1 times B minus 1, which is what the degrees of freedom we'd have left for error. So then we can also calculate our sum of squares block, treatment, and error. Those should sum up to our sum of squares total. And just as before, sum of squares over degrees of freedom gives us our mean squares. Our mean square error is our pooled estimate of variance. And then our F statistics, there's one for the blocks, one for the treatment, and each of them look at the corresponding mean square divided by the mean square error. So from this ANOVA table, we can test whether there's a block effect or a main effect due to the block variable. Our test statistic follows an F distribution with B minus 1 numerator degrees of freedom and I minus 1 times B minus 1 denominator degrees of freedom under the null hypothesis. The treatment effect is similarly distributed because our test statistic treatment follows an F distribution where there are capital I minus 1 numerator degrees of freedom, and then I minus 1 times capital B minus 1 denominator degrees of freedom under the null hypothesis. Both of these would be, as F tests, one-way tests or upper tail tests. And because we're looking at this randomized complete block design, we cannot test for interactions. The units within the blocks were randomized to treatment. It's not units at the were not randomly assigned to block and units. It was just within blocks that are randomized to treatment. So we can't really can't look at the interaction between our block and treatment. Just as in the the one-way ANOVA setting, we can also test for specific contrasts and all pairwise comparisons using the least significant difference or using the Bonferroni method. And the use of these in the randomized complete block design setting is a very straightforward extension of what we did in the one-way ANOVA setting. So that is pretty much what you will be responsible for test 3. I will hear from you on Friday, and good luck on the test. Take care. Bye.